All right, well, let's get started, shall we? Welcome to another Sunday meeting. This will be Pwn 3. Usually this is out of order, but we are doing heap exploitation a bit earlier this time, but that's okay. You do not need to do raw. But this Thursday, Keela will be giving the raw meeting. And this weekend, LACTF will start. We will be once again commandeering a room in Siebel and doing the CTF over the weekend. It starts the 16th at 10 p.m. Yes.
So does that mean we're meeting at 10 p.m. on Friday or on Saturday?
We will start, and if people decide they want to congregate at night in a building, then we will announce. Most likely, we will probably be like on the Saturday at like 10 or 11, get a room. AM, 10, 11 AM. All right. This is meeting flag, house. Finally, a relevant XKCD, not one that I've used 4 times. And also a really old one because it's one of the few ones where he uses color.
I haven't actually seen this one.
Yeah, this is like number like 138. I don't remember. It's like very, very early.
How to heap so many times.
Because I want to make sure people really know that that's the site that they should go to. That is the Bible. There is something called the Heap Bible, but how to heap is the actual Heap Bible. There are 2 Heap Bibles.
Which Bible do you read? Yes.
There's a schism in heap exploitation. Okay. So quick recap. Memory layout. At the top of memory, we have the stack, and at the bottom of memory, we have our instructions. But right under the stack, with a fair bit of space, is about where your programs place the heap. The heap is where we're going to store memory that we want to use during our program. So we've seen static stack allocation, and in C99, C also supports variable length arrays. So you can provide variables on the stack that have either a fixed number or a parameter number and get a array of that size. But the issue becomes of how do we return an address to those buffers? Because if we try to return the addresses buff2, the stack frame gets cleaned up. Now that's garbage data. We can't trust putting any data in there without a different function and clobbering things within it. So this introduces the heap structure, which is not a heap data structure. It actually has nothing to do with heaps. Everything in here, there's no keys, key pairs, or things like that. But it allows us to do dynamic memory allocation. So these allocations are preserved across function calls, and it's up to the programmer's responsibility to pass pointers around to those allocations of memory. So the 2 functions that you use are very simple. You have malloc, which takes in a number of bytes and returns a pointer to a chunk of memory of at least that size, and then free, which frees the allocation back up so you don't. So when you're done with it, you can clean it up. You don't leak any memory. On 64-bit systems, regardless of what you put in that size parameter, you will always get a chunk that is at least 32 bytes large, with 24 of those bytes being usable memory. So you can't like allocate 4 bytes. Everything is at least 16 byte aligned on the heap, and the minimum allocation is 32 bytes. This is for 64-bit. For 32-bit, everything shifts down by a factor of 2. So using heap, very simple. You like receive a pointer from malloc. I'm being lazy here because malloc's return type is actually a void pointer, so you would want to cast it. This is using implicit casting. Your compiler would yell at you. You can store values into it like any other pointer. You use size of to get the right factor of bytes you want to allocate. So an integer is either 4 or 8 bytes, and then you would multiply it by the number of elements that you want. And this allows you to treat the pointer like an array. And then when you're done with it, you can clean up that pointer by just freeing the buffer. If you take 241, you will become 341. If you take 341 or 340, you will become vehemently aware with the pains of using pointers. I do not have time to reteach everything, but I hope that this is just cursory enough to understand basic pointer and memory usage. So the basic model of the heap is actually quite simple. There's this idea of the top chunk. Your program will immediately reserve like 3 or 4 kilobytes of memory just to have ready to be used for allocations. And so when you call malloc, it will break off a bit of that top chunk to create your first allocation. And when you create a second allocation, it will again break off some of that top chunk. So both of those allocations will be right next to each other. And those allocations have some metadata which give them your size. So you kind of have like a singly linked list of allocations all in a row. When you call free on a chunk, that will mark the chunk as free. And if you call malloc again with a similar size, it will just reuse that allocation instead. So that's how malloc stays efficient, is that when you free memory, it kind of remembers what allocations you did in the past, and if it can reuse it, great. If not, it will break stuff off of the top chunk. So what happens when you call free on a chunk? Because this is kind of like the major aspect of why malloc is really complicated. So when you free a chunk, it gets added to some free lists, just like some data structure that keeps track of free chunks in the program. And because you don't necessarily free chunks in order, this is a secondary list on top of everything that's keeping track of all the available free chunks. So if you malloc with a similar size, it will retrieve it from the free list and just give you back that old allocation. And glibc has tons of optimizations to deal with this. And so we're going to discuss something called bins, which are these types of free lists. And depending on the type of bin, it will be implemented as a doubly or singly linked list. When you free a chunk, some extra metadata gets placed into that block of memory to provide malloc information about that allocation and adjacent allocations and previous and next free chunks. So this is kind of like the anatomy of, yes.
So if the size of the chunk that you want to reallocate from the free list is not exactly the same, does it just break off a chunk of that or allocate more?
So it depends. So if it's very close and the chunk available is slightly larger, it'll just give it to you and it won't change the size of the chunk. So like, even though you might request 24 bytes, if there's a 32 byte one available, it'll just give you that one. It doesn't care. You won't ever notice. And technically you could overwrite a little bit and not cause any problems, but that's the magic of C. If there's a very large block available and that's the only available block, in some cases, yes, it will create an allocation of the size you requested, split the chunk into 2 and create a new free allocation and put it into an appropriate list.
What about smaller?
The
block that you're trying to get is bigger than the value that's in the free list.
In that case, it would rip it off of the top chunk. It has to make a new allocation. So this is the anatomy of an in-use and free chunk. So the pointer you get from malloc is just 8 bytes past the actual pointer that you receive. You see the previous size fields. In modern malloc, they are very much unused, like most of the time. So they never actually show up unless it's like very specific circumstances. So this top 8 bytes here just has metadata telling you the size of this chunk. And because malloc is 2 byte aligned, these last few bits are used as flags. So you can see whether this chunk actually corresponds to a memory mapped chunk using mmap, which is a whole another host of issues. Whether the previous chunk is in use or it tells you about the allocated arena. We are not talking about arenas. It has to do with multi-threading and malloc. All you have to know is that we're all operating within the main arena on single threaded with a low thread count programs. But when you free a chunk, what it does is it fills it with forward and back next size. Again, the forward and back next sizes are only used with really large chunks. But the important part is that pointers to other free chunks are stored in free chunks, which is what allows it to be efficient. There's no explicit like node-based linked list. The chunks are the nodes when they get freed. So this brings us to coalescing and splitting, as Julius brought up. When a bunch of free chunks are adjacent, malloc will occasionally just coalesce them all together into one big chunk. Some bins are designed around being fast, and so they will prevent coalescing. And some large chunks, if it's the only chunk available, will get split into two chunks, and then the remainder chunk becomes a new free chunk. If a large chunk is adjacent to that top chunk that I mentioned, the malloc will sometimes coalesce it with the top chunk, so it just kind of disappears from all of the free lists. And again, when the top chunk gets too large, then malloc may decide to just unallocate the memory altogether, because there's a system call that actually requests memory from the kernel as the heap grows. It's a very slow function, so malloc tries to prevent calling that function as many times as possible. So in the case that you do have a lot of unused memory, it will release some of that using that function with a negative parameter. All right, so bins, I've mentioned this before. It's basically a bunch of singly or doubly linked lists that maintain all of your free chunks within malloc. We want free chunks to be efficiently available because there's no real hash map implemented for chunks. And so if you know traversing singly linked lists can be order n to find good chunks. So we don't want to spend linear amounts of time to get an allocation, especially when we have high performance programs that, you know, are constantly allocating and deallocating memory. Although it is funny though that because this function is a bag of weasels, NASA's coding guidelines for rovers say do not use malloc. Everything is allocated on the stack. So we're going to talk about all the bins that are within malloc's state. So the first one, and this is kind of one of the more recent implementations, is Tcache or thread-specific bins. There are 64 bins. Each bin has an associated size for the allocation. The minimum is being that OX20, and the max size ends up being OX410. The amount of useful space is minus, you know, 1 word. Each thread gets a new Tcache. Again, not important. A lot of what we're going to be introducing you to is just single-threaded applications. But each of these Tcaches, each bin can only hold 7 allocations. So they're meant to be really high use, high revolving allocations. And these lists are only singly linked, which is important to understand for exploits in the future. But there isn't any backwards pointing, and it's kind of done in like how the allocations go in and out of the Tcache is more akin to like a stack. But because they're meant to be super fast, they kind of forego a bunch of security checks on them, so they're very easy to exploit. You have a question, or you
Do
just
you want to explain why the libc version is important? That was something I was confused on.
Oh yeah, so libc, your standard library when you import your functions, is a file that gets updated every so often. And every so often when Canonical wants to update their version of libc, they'll pull down a different version. In each version, they're improving and securing and hardening the libc to prevent exploits, to provide new features, and so on and so forth. So any version, so glibc version 2.25 and before, Tcaches just don't exist. They are not implemented in malloc. This was something like added as a new feature in 2.26 and beyond. I think right now the latest version of glibc is 2.39, and Ubuntu 22.04, which is what most people are on if they're like grabbing Ubuntu off of the internet, is on glibc 2.35. And so a lot of malloc exploits will change slightly depending on which version of glibc you're on as they implement more patches and whatnot. Okay, so kind of the more natural form of bins are just fast bins. This now acts as like an overflow to the T cache. If a allocation can't go into the T cache, it will see if it can go into the fast bins next. There's only 10 of them, but I found out last night that sometimes malloc will only let you use 7 of them. It's very interesting when it decides to use the fast bins or not. The important part here is that in use bit that is free bit is kept on, even though it's in a free list. That's because malloc will look to coalesce free blocks together, and it doesn't, and the fast bin wants to prevent coalescing, so that they still become available and you don't have to split blocks later. Again, this is another singly linked type of free list. So then we get into kind of like the masses here. So the bin almost every allocation will go into first is the unsorted bin. This is your laundry pile of memory chunks. When you free something and it doesn't go into the T cache and it doesn't go into the fast bins, it will just end up in the unsorted bin. Malloc, while it being one function, is a very complicated state machine under the hood every time you call it. So even though this allocation ends up in the unsorted bin, malloc will just sit and wait for the next malloc call. And if it can give you this allocation back immediately, it will, because that's pretty fast. The unsorted bin shouldn't have that many allocations in it. If not, it will put it into a small or large bin, depending on its size. And those small and large bins are sorted. So small bins like fast bins have a fixed size in every bin. So there are 61 bins, each of them have an associated size. Chunks have to be of that size to fall into that bin. Coalescing can happen within the small bins, and it's a circular doubly linked list. So each chunk will point forwards and backwards to the next chunk in the free list, and at the end of the free list, it points back to not the first chunk, but the pointer where the array is held. So it kind of points back to where the free list's pointer is held. So that's small bins. Large bins carry everything else. It's kind of the idea of we're gonna store roughly the allocations, because at this point we're talking like allocations that are, you know, like 3,000, 4,000, 8,000 bytes. And so the difference between allocations of 8,000 and 8,016 bytes is not that much. So each bin stores a small range of memory allocations in a sorted order. And it kind of does this having tree-like partition for the bins. So the first 32 large bins, the difference in ranges that it will store is all 16 bytes. And then we go to the next 16 bins, and the difference in ranges is all 64 bytes, and so on. And so like the final 2 bins, the difference in ranges between those 2 bins is 256 kilobytes of allocation memory. And then there's one just everything else bin if you just have massive allocations. Each of these, again, are circularly doubly linked within each bin. And so that kind of covers all these binnings that malloc will do depending on what is free, how large it is, what's adjacent to. So now we can get to another basic model of the heap. So we can have a bunch of allocations. I'm kind of ignoring that coalescing might happen here. And the T cache has a few bins. This refers to the size that it's tracking. Each of these will point as a single linked to a chunk available. If the T cache is full, you know, it will end up in the fast bin here. Small bins are these circular doubly linked, so C will point to D. I didn't double the arrows, sorry. But then D will point back to like this pointer up in where the bin is. Large bins, again, kind of have these like separators in terms of what size it stores. And then we have this kind of like out in the wilderness unsorted bin that will get dealt with on subsequent malloc calls. Okay, I also wanted to mention that there are 2 other functions that are related to malloc. We have calloc, which takes in 2 parameters, an item and the number of items you want and the size of each of those items. What calloc will do is it will clear out all of the data to 0. This is particularly important if you're allocating a bunch of structs, because the structs will have fields. You don't want to pre-initialize them with accidental data. Not to say that couldn't happen with just allocating integers, but because of the structure of calc, a lot of people will usually use them when dealing with structs. And then we have realloc, which is an even more horrifying function because it will do malloc and free under the hood. It will you give it a chunk pointer and a new size, and it will reallocate the chunk to a bigger size. So if you don't change the size that much, it might just return the same pointer. If it can coalesce an adjacent block, it again might return the same pointer. If not, it will find a new chunk to give you, copy all the data over, and give you the new pointer. That might split blocks, it might cause a new free block. Realloc sucks. It's so hard to like understand what it does if you ever see it in an actual challenge or on a target platform. And so, yes.
So just from before, how come calc is the only one that doesn't use Tcache?
I don't know. They decided that Tcaches wasn't important. My guess is that Tcaches got implemented and it was only implemented within like the malloc structure. And frankly, it's because malloc is thread aware, but not thread based. So like it will know that there are 13 threads, and that's all it will know. And each of those thread caches, calloc doesn't want to accidentally take them and then like screw someone's thread cache up because you have a bunch of mixed states here. Yeah, it's just calloc will just not use the Tcache. But yeah, there's tons of optimizations within malloc, and it would take an entire semester to just go through glibc's malloc, which is why it's funny that like, you know, you're given 2 weeks to do it in 341. But yours in 341 will suck. So who cares? Because like all malloc technically needs to do is return you pointers, and free can do nothing. That is a valid implementation of malloc. But the best way to understand malloc's memory allocation, freeing, coalescing, splitting patterns is to just experiment on the target software you're given. Especially because between glibc versions, these optimizations might change. You don't know what you're gonna get when you malloc 3 chunks, free a few, and what the state of all the bins end up being. When you go through a debugger, there are tools to inspect the heap state. And we'll cover those in a bit. So changing gears for a bit, I want to talk about exploiting programs when we're doing binary exploitation. Our goal is arbitrary code execution. We want to control the return address on the stack, usually, to give us a jump to somewhere unintended, usually the glibc library itself, because there's a lot of useful functions and there's a lot of useful gadgets. We'll talk about gadgets next week, and how return-oriented programming works. So there's 2 primitives that you need to get there, and these are the strongest 2 primitives that you will work with. It's arbitrary read and arbitrary write. How do I read from an arbitrary position, and how do I write arbitrary data to an arbitrary position? And so this allows you, if you have an arbitrary write to the stack, you can overwrite the return address. It doesn't even matter if there's a canary, because if you can choose where to write to on the stack, the canary is only blocking buffer overflows, right? If you're just able to overwrite the return address by addressing it, then canaries don't matter and you get control flow. And likewise, getting an arbitrary read, we can get those libc base addresses to defeat address space layout randomization, and know what we want to write to our return addresses. And so this is what kind of separates heap exploitation from things like buffer overflow and return-oriented programming. Those strategies are the final step in an exploit chain. Those already give you the primitives. The things that we'll talk about in heap exploitation is building up to a primitive to then finish the rest of your exploit chain. So heap won't necessarily just cause RCE. This just gives you the tool to like set forth the last step in your exploit. So there's this kind of idea of several structures within a program, and you want to leak addresses from each of these, because address space layout randomization will randomize where each of these are, and if you want to be able to read or write in each of these structures, you're going to need to leak them. So if you're in the heap, the free chunks, the last next pointers, remember where I said it points to like where the free list starts? That's in the main arena structure that libc holds. So the last next pointer in a structure will really point to libc's a pointer stored within libc. And likewise, libc, those bin addresses are then pointing back to somewhere in the heap. The stack, usually the only way you're leaking the heap from the stack, from reading something off the stack, is some saved pointer, because presumably you're allocating off the heap, saving it to a variable, passing it around. Between the stack and libc, libc has a symbol called environ, which points to where environment variables start on the stack. So that's very useful if you need a stack leak and you could read somewhere off of libc. And likewise, the stack will usually have a return address to the libc start main function, which is what like initializes your program, and so that gives you a leak to libc. So it's important to understand that when we're constructing these arbitrary reads, we know where we're able to read from and what that lets us leak out. So the first exploit we'll talk about, or bug really, is a use after free. When you free a pointer, that's all free will do, is just free up the pointer allocation and update malloc state. You still have a variable that points to an allocated, well, now free chunk. And that free chunk has metadata meant for malloc's use. But nothing is stopping you from writing or reading to that pointer after you've freed it. So this allows you to kind of screw up malloc's structure. You can either preload chunks with data, which might cause logical errors in the program. You can modify chunk sizes if you can index through your pointer and affect other chunks. And you can modify forward and back pointers, which is really important for tricking malloc into giving you a chunk where it shouldn't. So I want to show an example, and this is called T-cache poisoning. So we start with something simple. Two mallocs, we get two allocations A and B. All right. And what happens when we free them is that they get inserted into the T-cache of the associated size. And again, T-caches kind of work like stacks. So A gets put out at the end of the T-cache here, and then B gets inserted at the front. And so let's say that we have a use after free on the variable that stored the pointer to the allocation to B. That means the first entry in B is a next pointer, because it's a single linked list. It just throws in one address that points to the next pointer. So we overwrite the forward pointer on B to say a stack address. So now our T-cache looks like some free chunk, and then it points to some address on the stack. Our choice, let's just assume we have one. So then what happens when we allocate is we first allocate back our B allocation. And then when we allocate again, we instead get a chunk on the stack. And we've just completely leaked A. Nothing points to A anymore, not within malloc and not within our program. Instead, now we have this nice little chunk up in the stack, and assuming the program lets us write or read from it, that could be extremely powerful. So that's T-cache poisoning. I believe one of the last, yes.
So what is it in this exploit that's specific to the T-cache? Like why couldn't you do this in a fast bin?
You could do it on the fast bin. It's the issue of the T-caches just take priority. Yeah. This is called fast bin duplication, or that's with double free. You could mess with it with the fast bins as well. I will say, if you try to do this exactly on the more later versions of glibc, even past the T-cache, you'll run into a small issue called safe linking. This was a small patch introduced to kind of protect the T-cache and free list. The heap challenge that's available on the CTFD does not have safe linking, so you don't have to worry about it. But what happens is the pointer that is stored in that chunk that itself is an address, right? We're storing a pointer in an address. What safe linking does is it will mangle that pointer with the position that it's stored in. All right. And so you kind of encrypt it with the address-based randomization of the position. But if you're going from a fresh program with small allocations, the position that the pointer is stored in and the pointer itself are in the same memory page. So you can just unilaterally decrypt it because the bits that were used to encrypt it are part of the pointer. So it's kind of goofy. This doesn't really fix anything strongly, but it does require you to leak an address from the heap, which will make it a bit harder in more modern Pwn. But usually if you're able to get as far as leaking something from libc or the stack, leaking the heap isn't that much of a issue. All right, so the next bug we'll talk about is double free. The free bit doesn't always mean free, which is a problem because it can kind of confuse malloc if you do it incorrectly. All this is saying is if I free a pointer and then I don't clear the pointer and free it again, malloc will just assume that you tried to free two independent chunks. It will try its best to like crash the program ahead of time. For example, if the top chunk in a list is already freed and it equals the pointer you just tried to free, it will crash. But if it's not the top chunk in a list, then it has no idea. It doesn't scan the list except for the T caches. So this allows you to free a chunk twice, alloc that chunk back. Now you have a chunk that you can possibly modify the data of, and also it's affecting the metadata of malloc state. So if like T cache poisoning, if you double free a block, alloc the block back, write a pointer into it, and then alloc again twice, what will happen is that you get some forged chunk onto the stack or onto libc, something like that. It's very similar to use after free, and can be caused by a whole host of logical failures. You as programmers, anytime you call free, just null out all references to that pointer unless you're doing something really specific. All this could be heavily avoided by like safer memory allocation patterns. So I have forgotten about this slide. All right. Whatever. This is why you don't write meetings at 3. Again, the goals of Heap Exploitation is you want to make malloc return a chunk to somewhere interesting, like the stack, or maybe global variables, or maybe somewhere in libc. You want to be able to write values to arbitrary addresses. It doesn't cause RCE, it acts as a primitive to get to RCE. There's also really weird like end goal ones. You can like unmap libc with malloc because your program will load like the virtual memory map to libc, and if you can trick it into thinking it's a chunk, it can just completely unmap your system libraries, and it makes the program do really weird things. But that's just the goals with Heap Exploitation. So let's just look at what a complete model of Heap looks like from 4 years ago. It's still bad. So I have resources available to you. This stuff is not easy. This diagram was not meant to be readable. Heap is very hard, and I was only able to learn it over this past summer by just almost pure brute force. You really have to experiment a lot and kind of sit down and work with available material and look at past CTFs and CTF write-ups. And so when you're working with these programs, if you use Pwn debug, I can tell you about a few very useful commands that Pwn debug provides. If you use Jeff has similar ones as well. Heap will just display the state of the heap, all the currently allocated and free chunks just in a sequential list. It won't show the data at these chunks, but it will show the addresses. You can also type bins or the type of bin, and it will show you the state of each of those bins. This is important to let you know when you've caused like a double free, what ends up in which bin, depending on the memory allocation and free pattern. And a really useful one, and I was surprised to find out about this, is viz heap chunks. What this will do is it will dump a hex dump of the heap up until all the chunks that you've created, color code each chunk, and then let you know what each chunk ends up in what bin off to the side, which is really useful when you're working on debugging and developing heap exploits. You don't know what chunk causes what, especially if you're doing advanced things like changing chunk sizes so that you're overlapping with other chunks, and then malloc gets all sorts of confused on what to do. So resources, how to heap. Shellfish has a really great GitHub repository with a bunch of proof of concept C files that show off different forms of heap exploitation techniques, each of which are organized into glibc versions where they're valid. This page also has a bunch of extra tools and good heap resources for you to just go off of. I've also provided a few extra. The Zero Labs that we mentioned from the ARM meeting also has a few good pages about heap exploitation. There's also another good blog post. I would also recommend when a CTF comes and pass, look for write-ups about heap exploits because they usually use the same few tricks. Next meetings. So next Thursday we'll do ROP with Akil. This will basically be the last thing you would need to like be completely proficient, not proficient, but like pretty good at Pwn. Pwn is a infinite abyss of complicated techniques, and there's no such thing as being good at Pwn. And next weekend we'll be doing LACTF, so hopefully we will have lots of people that are able to tackle the Pwn challenges, and not just me. I believe in all of you. But yeah. Any questions?
Resource comment.
Resource comment, and then
Let's do the question first.
you.
Oh, yes, so this is a more general question, but in terms of the arbitrary right, I know if there's partial railroad, yeah, a quick win with the global offset table.
Mhm.
If there isn't, do you have any suggestions that work, or is it entirely program dependent?
Usually in that case, you're doing return-oriented programming. So that would be, so as a gist, the idea is those returns instructions that exist anytime you return from a function, there's a bit of useful assembly right before that return. And so you can inject a bunch of return addresses on your stack, run a few bits of useful code, and get somewhere interesting. libc, being a massive system library function, has so many gadgets that you can pretty much do anything you want, including there's something called one gadget, which is return to this address with these registers in this state, which is usually just 0. And it will just do a system bin sh, like right off the bat, as just one return address. So the goal, if you don't have global offset table, the goal is to then return to interesting bits of code, or maybe there's a one function.
Yeah, another thing for that, you can also, I don't know if this is true for the latest like glibc things, but you can also write to function hooks that are in glibc, like
Yes.
free hook or malloc hook that get excited whenever you call free or malloc.
Yeah, so there's injection hooks. The idea is like, oh, you can customize your malloc and free like if you need in your program, which nobody used except for hackers, because you can just they're always called before free or malloc. They have since been removed in the latest glibcs, but I think anything before glibc 2.32 will still have free and malloc hook.
Just to confirm that, because all the bins you mentioned have sizes. So for example, if I free 1,000 chunks consecutively, the rest will just end up in the unsorted bins.
If you free what consecutively?
If you free, for example, like 1,000 chunks consecutively, they just fall all into like the unsorted bin.
So the unsorted bin will not necessarily. Too many frees will cause malloc the C file, because malloc includes free, to eventually pull things out of the unsorted bin. Especially if you're freeing a lot of things in a row, if they're adjacent, it'll start coalescing and putting them into bigger and bigger bins.
What if they can't coalesce? Like,
Then you're making malloc very sad. But yes, if you malloc a large chunk and then malloc an 8-byte pointer and then malloc a large chunk and malloc an 8-byte pointer, it can't coalesce. It doesn't move small allocations around ever to make it easier to coalesce. Which is, you know, very intact, like adversarial against malloc. A lot of malloc's optimizations were designed around normal program expectations, so that's why, you know, very large allocations are not seen often, and small ones are reused a lot, because a lot of people are just allocating pointers to things.
assuming you don't run out of memory, does it cause some funky actions when the stuff gets too big, when the list gets too big?
Yeah, it's when the list or heap.
The heap.
The heap. So you've heard of the idea of Stack Overflow, the actual Stack Overflow. There is also a heap collision, which is when the heap runs into the stack. So if you do try to allocate too much and you're starting to get into stack addresses, it will just crash, because it's like, well, now you've crossed two memory, like, because the virtual memory mapping knows where the stack is, knows where the heap is. If they ever start crossing, it's like, whoa, stop that immediately. There's, with the Stack Overflow, I don't think there's any bounds on the heap, but there is a bound on how large the stack can get. So that's why Stack Overflows happen. It's more like a setting that happens. I might be wrong in that.
So you mentioned a lot of like the heap information is stored in ellipses space, right?
Mhm.
So if that get too big to crash the program?
No, if you were kind of counting, you'll notice that between the unsorted large and small bins, there's exactly 256 bins. Or unsorted large, small, and fast bins, there's 256 bins.
So it's fixed size.
It's a fixed size of, like, it's one struct for the main arena, which defines the heap. Cool. All right.
Oh, for my learning resource, you go to the learning resources channel. There's a Udemy course called Heap Lab that sort of provides step-by-step GDB commands and like a live challenge you can walk through. It's quite nice. Would recommend checking it out if you're interested.
Yes.
That's in the learning resources channel on Discord.
One of the things you'll learn is that each type of heap exploit is called House of something. I don't know why, but there's like House of Force, House of Banana, House of Eisendrosh. I probably could just start saying random syllables and almost be right. There's House of Blindness, House of Nightmare. Yeah, I don't know. I don't know where this came from. One day I'll find the origin of it, but when you see in CTFs, and they'll be like, we did House of Blank. It just refers to some heap exploit usually. So yeah. Cool. I moved Ravi's heap challenges over to the latest category. There are version the first few shouldn't need you to do anything of ROP. It's a lot about causing logical errors with heap, use after free, and double free issues. So you should be able to tackle most of them, and I'm happy to help for the rest of the meeting. I don't know how long I took. 45 minutes, which is good enough for me. All right.